All right, hello everybody. Welcome back to 112. Sorry about the slightly late start. My computer decided to have a few issues here right at 3. So hopefully, oh, hi kitten. Hi Cecil. Hopefully this will work and you guys will be able to see me on Twitch and or later on YouTube. Okay, so today's topic is atoms. We are kind of starting to really get into what's considered modern physics, where we look kind of beyond the scope of just like I've got a ball and it's falling, or a car is moving, or things like that. And we're starting to get into the realm of the really tiny stuff, right? So atoms are super tiny. We can't see them with our eyes. Today we will deal with those, and then next week we will deal with the nucleus, which is even smaller. And inside, Cecil, cat, pick a spot. The nucleus, which is inside the atom. Okay, so let's get started. Okay, so let's think about what an atom is. Okay, and we're going to go through a couple of different iterations today in terms of how do we model the atom? Like, how do we describe it? What do we think is happening inside of it? And why, right? What's the experimental evidence? So today is actually kind of a lot of almost storytelling in that sense of like, what is the story of the atom? Okay, so we know the constituent parts at this point. We know that an atom is made up of 3 different kinds of particles. Protons, which are positive. So a proton, I will write as P+, P for proton, and plus because it has a positive electrical happening inside of it. And that was Cecil. Thank you, Cecil. I think he's done. Okay, so they have a positive electrical charge. Proton starts with P, so we call it P+. The number of protons in an atom gets the letter Z. Okay, so this is like the shortened form of, instead of writing proton, we can write P+, and then Z is how many are there. So if there's 5 protons, Z equals 5. All right. Protons are important. They're positive. We also know there are electrons. So electrons we'll call E-. Assuming that the number of protons and electrons are the same, then you can use Z for either, although we usually stick with it with protons. Oh, and I kind of didn't mention, but the protons we know tell you which atom. That's why it's important to know the number. So if Z equals 1, it's hydrogen. If Z equals 5, it's boron. If Z equals, I'm running out of the ones I know off the top of my head, 6, it's carbon, etc. The electrons will tell you whether it's neutral or an ion. So if these are the same value, right? Positive and negative, if we have the same number each, it's electrically neutral. If we have fewer electrons, it'll be positive. If we have more electrons, it'll be negative. Okay? Electrons are very important for chemistry. Chemistry is all about what are electrons doing, what is their behavior, how are they interacting with each other. What we in physics tend to care about is how are electrons like interacting with the protons and that kind of stuff. Okay, and then the last thing is we have neutrons, which are neutral. So I will write them as N with the 0 because they don't have charge. Okay, just they themselves have no charge. And their number, the number of neutrons, gets a capital N. And they tell you isotope, which we'll talk more about, and they help between the neutrons and the protons, they help you determine the mass of the atom, and stability, which we're going to deal with a lot next week when we talk about radioactivity. Okay, so that's cool. We know a lot about atoms. Come on. I feel like it's just being super laggy. Okay, so we know a lot about them, but one thing you can ask yourself is how do we know any of this, right? Also, hello, Frankie, and anyone else who happens to be here, but Frankie said hi. Okay. So we know the different parts of the electron, or of the atom, but you might ask, how do we even know that atoms exist, right? I mentioned at the very beginning, atoms are too small to be seen. Well, we actually know about them basically because of chemists. Okay, we got to hand this to the chemistry people. They got this figured out. So some things only make sense when you have atoms, things like the periodic table, where each element is a distinct type of thing. And what that thing is an atom. Okay. Other clues that they had that they worked from were things like these mass ratios. So here's a picture of the water molecule. You've got oxygen and 2 hydrogens. And they did experiments where they converted this into oxygen gas and hydrogen gas. And what they found were these ratios, right? The mass of oxygen is 16 times that of hydrogen. But there were 2 hydrogens, so you would get 8 times as much mass in oxygen as you did hydrogen, no matter how much water you started with. And so that kind of fundamental relationship between how much of these there were came down again to this fact that, well, oxygen must have some thing there that is itself oxygen. And the name atom came from this ancient idea of an indivisible piece, like you can't split it up into smaller pieces. Now, we have already split our atom up into smaller pieces, so it's not necessarily the best name, but it'll do. Okay, so we know that we have atoms. The mass ratios were an important clue, but just generally the way chemistry works, you can't explain it with other models. Atoms are where it's at. Okay, so if atoms exist, how do we know about all of these other pieces? So first of all, here's an interesting thing about electrons. Now, you guys have already used electrons when you've been thinking about electricity, right? We talked about how there's positive charge and negative charge, and in reality, the negative charges move. But in our model of electricity, we were pretending it was the positive charges that moved, right? So we know that negative charges, the negative electrons, are important. How do we know they exist? So some of the first experimental evidence were these things called cathode ray tubes. And let me pull this up. The link is there on the slide, so you guys can always watch this later. I've got the volume down, but the subtitles are on here. But basically what you need is to see what happens here. So we've got this device. It's essentially a metal tube, or a glass tube, and it's empty. There's a vacuum inside. And then when you turn electricity on, we get this beam inside. And that beam is actually literally electrons that are moving through the glass tube from one metal plate to the other. And then because they interact, there's actually a little bit of gas in there. Because they interact with that, it lights up, we can see it. And what was interesting is what he's doing here is with a magnet. So this beam of electrons is deflected by a magnet. It changes direction. And that means that it's being pushed or pulled on by this magnet. Now, we kind of skipped magnets in this class because we didn't have time. And we had other interesting things to talk about. But generally, the idea is, we talked a little bit about magnetic fields with light. And magnetic fields will have a similar, not exactly the same, but they can have a similar effect on electrons where that an electric field can have. So an electric field will always push or pull on an electron. A magnetic field pushes or pulls if the electron is already moving. And these electrons are moving, so you put a magnetic field near them and they change their direction. Okay? And so physicists were able to use this to figure out that they were negatively charged, and they figured out their mass to charge ratio. So how much mass do you have per amount of charge? And then with other clever experiments, they were able to figure out those actual numbers, not just the ratio. So the numbers are important. I'm going to go ahead and list them here as well. So we've got two numbers. We've got the mass of the electron. It's 9 times 10 to the minus 31 kilograms. That is super tiny. Electrons are one of the smallest things that we know about. And then the charge of the electron is this 1.6 times 10 to the minus 19 coulombs. Oh, and they're negative. So the negative sign. Okay. And those numbers are, okay, that's a number. But we'll be able to compare that to some of the other numbers. Okay, so we know there are atoms mainly from chemistry. We know there are electrons mainly from circuits and experiments like I just showed you. How do we know about neutrons? Neutrons are interesting because they don't have charge. So like the electrons we were able to figure out because they're charged. Charges react to electric fields and magnetic fields. Neutrons don't. They aren't charged. They don't feel that force, okay? So how do we know about them? Again, it kind of comes back to chemistry. So when we look at an element, we can look at their mass, the average, whoops, wrong thing. Click on this. The average mass that they have. Hydrogen, okay, has a mass of 1. Helium, a mass of 4. Carbon has a mass of 12. Nitrogen, 14. Oxygen, 16. Okay, so far this makes sense. And these units, by the way, atomic mass units, are essentially, it's in terms of the mass of the proton, okay? So we have essentially 1 proton's worth of mass in hydrogen and 16 protons worth of mass in oxygen and 23 in sodium and 35.5 in chlorine. And that's where things get weird. For small numbers, for small elements on the periodic table, this makes so much sense. Protons, like we have these integer numbers, right? We have these tiny pieces that come together to form the element. And so if you have 16 of them, you have a mass of 16. How do you have 35.5 of them, right? Can we split a proton in half? No. I mean, unless you start talking about quarks, but that's beyond the scope of this class. So that's not what's going on, right? Okay, so before we kind of dig into the solution to that and talk about why neutrons help us see that, I want to talk you through kind of the historical process, right? Story time, physics story time, of how do we develop our models of the atom, and then how did we kind of figure this part out, okay? All right, so let's start with Thomson's model. Thomson knew at the time, and this was late 1800s, okay, early 1900s, just to give you an idea on time. He knew that atoms could sometimes be charged, right? Everybody knew this. So they knew about the existence of positive and negative charges. And they knew that most atoms, most elements were neutral. So how do you make neutral when there are charges? Well, you just have to have equal amounts of positive and negative. So that wasn't too big of a problem. The issue was, how are those arranged? How do you put your positives and negatives inside of your atom? So Thomson said, well, maybe we have some kind of positive goopy background, and then the little dots of negative. Because again, they knew, they were pretty sure about electrons, and they knew that they could have small particles of negativeness. So that's what we'll do. We'll have just a big positive smear, and then like a sphere, and then we drop our negatives in. And it's kind of like bread with raisins in it, okay? The bread would be positive, and the raisins would be the negatives. So that's the original model. The problem with this was that there were some other mysteries going on. So uranium, somewhat famous radioactive material, you could have a rock of uranium, and it would just on its own, because it felt like it would emit different rays, okay, different beams of stuff coming out. And the first kind of ray that they didn't know what it was, they called alpha rays. So alpha is the first letter of the Greek alphabet, and so it's kind of like giving it a variable name. We'll call it A, because we don't know what it is, but we'll call it A in Greek, okay? So the alpha ray, all they knew was that it was positive and relatively heavy, okay? And that was being emitted by uranium for some reason. And then the next type that they called beta, like B, were very fast, negative, and lightweight. And in fact, they were able to figure out these must be electrons. Okay, cool. So we definitely have electrons coming from elements. So Thomson's model is okay on that. We've got negatives in there. We don't know why they'd be emitted, but whatever. But why these big, heavy positive ones? Okay, so that was definitely unclear. And then Rutherford came along, and he did his experiment. Okay? So I'm going to redraw this. Rutherford took this uranium. So they knew that uranium shot out these rays. And so he has a hunk here of uranium. And they're really interested not in the electrons, but in the alpha rays, those big, heavy, unknown things. So every direction here, it's spitting out at random these alpha rays. Okay. And then what you do is you put blockers here, just like not included in this diagram, that's okay. So you put blockers there like made out of lead, something really dense, and it literally blocks these rays, but lets these through. So now you have a nice beam of alpha particles, and they are big, and they are positive. And then what he did was he put a thin sheet, like foil, like aluminum foil kind of stuff, except it was made out of gold. So he's got a sheet of gold foil here. And the reason for this is because they were testing to see how these big positive alpha particles would interact with the atoms inside the gold. Okay? And what they expected to see with the Thomson model, so Thomson's model has these negatives kind of in it, and we're sending a pretty big positive this way. But because this is positive and these are negatives, like generally speaking, this is not going to interact very strongly there. Like a lot of the pushes and pulls get canceled out. So if it got kind of pushed one way or the other, it would end up being by a pretty small amount, maybe like that, or maybe it just kept going. That's what they expect to see. These are the results that Rutherford expected. And so basically they were like, yeah, these alphas are going to come in, and some of them will go up a little bit, and some of them will go through, and some of them will go down a bit. And so if we put some detectors, like here, something where when this particle, the alpha particle hits it, it'll like ping it, like leave a little dot or something, some way of knowing that something hit it there, they can detect it. And that's what they did, and that's what they saw. So The detectors here, you get these what were called small angle deflections, because this angle here might be like 1 or 2 or 3 degrees, or maybe 5 or 10. Those are pretty small numbers, small angles. So this small angle deflection is what they expected from the Thomson experiment, or Thomson model. But Rutherford wasn't done, okay? He had this here, and he saw what he expected to see, and then he kept looking, okay? And so he put his detectors here and here, and now we're getting to kind of medium angle. Now we're looking at maybe like 30 degrees or 45, or maybe even like 70 or 90 degrees, okay? These are fairly big angles, which, if this model is correct, you would absolutely never expect to see, or very rarely get an alpha particle to go up there. But they measured some. Okay, so they have actually measured some now that go that way, which means that when it came through the gold, it deflected at a fairly big angle like that. That's unexpected, but he wasn't done, okay? So then Rutherford looks back here, and when he looks back there, he still got results. So sometimes these alpha particles come in, they hit the gold foil, and they bounce backwards. Huge angle deflection, like up to 180 degrees. That is enormous, okay? And absolutely never predicted by the Thomson model. So here's kind of pictures of what's going on. On the left here is what I was showing you guys with the Thomson model. A lot of those positives and negatives, their influence kind of cancels out. You don't really see a big effect. But we do see big effects. We see an alpha particle come in and bounce backwards. And so the model that replaces the Thomson model is the Rutherford model for the nucleus. And he was the first one to say, hey, maybe the atom is actually made up of a tiny center, the nucleus, where you're going to have positive charge, and then electrons, the negatives, which are kind of outside of that somewhere, to give you the bulk of the atom. Because that explains these results. If you have this nucleus, and it's positive, the alpha particle is repelled by positive. So if it comes and hits it like straight on, it's going to be like the two carts with magnets that hit each other. They repel each other and bounce back. And that only happens when you have something like a small positive, like all of the positive concentrated in one place. And so that's how we figured out about the nucleus. So we know about electrons. We know basically about protons at this point. In order to create a nucleus, you have to have your positive particles that all live in one place instead of like being smeared out. So we definitely have positive particles. We definitely have negative particles. Why do we need neutrons? And the answer is the answer to that question we had before about the weird massive like chlorine. So if you have hydrogen, that is our first element of the periodic table. It is 1 proton. Helium has 2 protons. We know that it has a double positive charge, but it has a mass of 4. That implies that it has 2 protons plus 2 of something else, which are about the same as a proton. Same with carbon. It's 12, but we know that it has 6 protons, so it must have 6 of something else. And that something else is the neutron. For chlorine, the reason why it's 35.5 is because it has 2 different isotopes. There are 2 different forms of chlorine with different numbers of neutrons. So both forms of chlorine will have 17 protons, but then sometimes it has a mass of 35, sometimes it has a mass of 37. So sometimes for the 35 it has 18 neutrons, whereas for the 37 it has 20. And that's the difference. They're both chlorine because the number of protons gives you identity. So with 17 protons, no matter what you do with its neutrons or electrons, as long as you have 17 protons, that is chlorine. But different isotopes have different masses because they have different numbers of neutrons. And neutrons have a huge effect in terms of mass and also stability. So that's going to be like the main point of next week when we do radioactivity, which is really fun, by the way, is looking at the effect of the neutron, how many neutrons and what happens because of that. Okay, so now we know there are protons, there are electrons, there are neutrons. We know that the neutrons and the protons have roughly equal mass, that they must live together. The heavy stuff has to be on the inside in that nucleus, because if it were spread out, this experiment would have gone differently. Okay. So now that we have that, we can start exploring even better models of the atom. And we're going to focus on hydrogen, okay? Because hydrogen is the first element. It's just one proton, one electron. It is the simplest atom. And if we can understand that atom, we can then apply that understanding to other atoms, okay? And by we, I mean like other people. In this class, we're just basically doing hydrogen. So a while ago, at this point, I say a while ago, last week, whenever it was that we talked about color, I said there was a fourth thing that we were going to look at for why it was red. And today we're looking at it. So the fourth thing is hydrogen gas. Unfortunately, I don't have my little lab demo thing to show you because it's on campus and I'm not allowed to go to campus. So we'll just have to look at pictures. But the idea is that if you take a glass vial full of hydrogen gas and you run electricity through it, the energy of the electricity makes it glow kind of a pinkish color. Okay, kind of red if you squint. And so that's another kind of thing, which is red-ish. And it's red for a fundamentally different reason than the apple, the red hot iron, or sunsets. So let's explore, why is hydrogen gas, why does it glow red? Okay, to do that, we need to talk about the Bohr model of hydrogen. Niels Bohr came on the heels of Rutherford and the others, and he helped develop not the best model, but a pretty good model of hydrogen. We'll talk briefly about the best model at the very end. Okay. But this is the model I expect you guys to know the most about and to understand the best. Okay. This is our very important Bohr model of hydrogen. Okay, so there's a few things that happen with the Bohr model. We put our positive proton in the middle because that's our nucleus. And then we have our electron out here. Now, electrons are negative, so they are attracted to the positive, okay? And this is going to be similar to something like the moon orbiting the Earth or the Earth orbiting the sun. And in fact, original kind of models were like, well, maybe the electron just orbits the proton. The problem with that is that if you orbit by literally traveling in a circle around, so if you literally move in a circle around like this, you're constantly changing your direction, which means you're constantly changing your velocity. Even if the speed stays the same, velocity is both direction and speed. So your direction changes, your velocity changes, you're accelerating. Okay, that's fine. I don't mind that. I have a force that pushes me this way. If I have a force and I have mass, the electron's mass, sure, I'd have an acceleration. What's the problem with that? The problem is that these are charged. And when you have something like an electron that has charge, accelerates, what it would do is it would give off energy in the form of light. So it would just always give off energy. And as it gave off energy, it would slow down, right? Like if you have kinetic energy and you're giving energy away, your kinetic energy gets smaller. And as its energy got smaller, it would start falling like that. So if you try to literally have an electron move in a circle around a proton, it does not work. It spirals in and crashes, and that's not an atom, okay? That does not work, so we're not allowed to do that, okay? We can't think about this. Fundamentally, we cannot think about atoms with the same physics that I've been teaching you all semester. It doesn't work. The stuff we've been doing all semester is called classical physics, and it works, like Newton's laws stuff, works really well on the human scale. Does not work at all on the atomic scale. That's why we need quantum physics. Okay, so the Bohr model is kind of our introduction to quantum physics, and he solves this problem of the unstable atom by saying, hey, you're going to have to exist in this circle. The electron is not moving around it. It just exists somewhere at this distance from the neutron. Okay? And it's not, and it might be at that orbit. We call it an orbit, even though, again, it's not moving around it. It's just, it is somewhere. Okay? And maybe it's not in that orbit, maybe it's in this one. But it's never in between them. Okay? So it could never exist along, like here. That's just not allowed. Okay? So this is how Bohr solved the issue of the electron like spiraling in. Is he kind of in some ways just was like, no, we won't let it. Okay. It has to exist. It could exist here or here, and it can jump in between, but it cannot exist in between. It almost has to teleport in a way between one state and the other without it doesn't live in between. Okay. So these are called stationary orbits. And the reason for that is because they don't change. Okay, this orbit that the electron can have when it's here does not change, even though the electron could shift to a different orbit instead. This orbit does not change while the electron is there. So that's part of the model. The other part is that the electron will emit light when it jumps from one to the other. So if it starts up here, as it gets bigger, okay, as these layers get bigger, they have higher energy. So this is going to be my high energy. And down here, this would be low energy. And so as I transition from high to low, it's think potential energy. If I have a lot of potential energy, and then I transition to a lower potential energy, from high potential to lower. In the classical case, I turn my energy from potential into kinetic. That's not what the electron does. It's only going to have the potential energy. Instead, it has to release it some way, right? It has to get rid of it. And the way it does that is with light. So to go from, like, for example, maybe this is like 10 energy down to 6, it would have to release 4 worth of energy. And it does that by releasing a bit of light. So it releases that. If you want to go from a small one to a higher one, you're actually going to have to eat that light instead. You have to get energy from somewhere. Usually you get it from light. Okay, so this light wave is emitted. And what's cool is that the frequency of this light wave depends on the energy difference. So depending on what the energy is up here and the energy is down here, you can get a different frequency of light. And frequency, if you remember from last time, is related to wavelength. It's related to color. So depending on the energies involved here, you will get different colors of light that are emitted. Let's talk about this equation that's here because it's really important. This equation says energy E. So this is the energy difference between orbits. Okay, so that's what this energy E is. Energy difference between orbits is going to be related to the frequency of the light. So F here is frequency of light. They're proportional. The bigger the energy, the bigger the frequency. Okay, so remember, big frequency is stuff that happens often, like this. That's going to be on the red side, or the blue, as opposed to red, which is less often and less frequent. So high energy is going to be related to blue, low energy is going to be related to red. And then there's a proportionality constant in between, H, which is called Planck's constant. It's very important at the atomic scale. Oh gosh, what's my -34? So it's a very tiny number, 6.63 times 10 to the -34, very, very teeny tiny number, joules times seconds. So it's an energy times time, which is good because frequency is 1 per time, right? So if my units here equals HF, for H we have joule times second, and for frequency we have 1 divided by seconds. So my seconds cancel and I'm left with joules, which is my unit of energy. So that's good. The units work. All right, here, did we talk about this? See, now I can't keep track of when I've talked about this. But when we look at our energy stuff, I already mentioned that the blue is the high frequency and high energy, and red is low frequency, low energy. Here's kind of my visual reminder of that, because this is related to why taillights are red. Okay, so taillights of a car are red because the people who see them are behind you. So if you're driving a car, you will see the taillights of the people ahead of you, right? And if they were white light, they would have more energy than when they're red. So low energy red light helps protect the night vision of you while you drive, because when you look at the red lights, it's just very low energy coming into your eyes. It helps maintain better night vision. Okay? It's just easier to look at. White lights for headlights have more energy because white is all of the colors. Yeah, Francie, we talked about a little bit. Yeah, I think here's where I had the pictures. I knew I had pictures for it. Because this is where it's related to as well. So, cool. White light has more colors, so it has more energy. And those frickin' blue headlights, that blue has the highest frequency, highest energy, those are the ones that hurt your eyes the most. Okay. So let's figure out why hydrogen looks red. We can draw, instead of having to draw the atom itself with the positive nucleus and then all of these different possible orbits, as you get to bigger orbits, you get to bigger energies. So sometimes we can just say, I don't care what the orbit looks like, I just want to know how much energy it has and just compare energies. So that's what this diagram is for. On this axis here, you have an amount of energy, and you're going to start from the lowest energy, and then up here will be high energy. And we're going to have these different levels. And I'm drawing them this in a way that's similar to what I have on there for a reason. And that reason is this is what they look like. Where as you go higher in energy, these get closer together in energy. So the biggest gap in energy is actually between the ground state. This lowest one is called the ground state. And up here we have our first excited state. Okay. Again, state is like orbit. Where is that electron? And then these are the energies of it. So most electrons like to live at the ground state. They like to have the lowest energy. It's like my tennis ball. If I set it somewhere high and it has a chance to like roll off and go somewhere lower, it will, right? If you bump it a little bit or something like that. Things want to be at the lowest possible energy. And so the same is true for the electron. Most electrons that you will ever measure, you or anyone else, will ever measure in hydrogen will be in the ground state. But sometimes they get excited. Sometimes we excite them. Okay, so for example, if we run electricity through it, we put a voltage across it. That voltage, that battery, gives it energy. Okay? So all of these electrons inside the hydrogen gas, we've given them more energy. So they started at the ground, we gave them more energy. Maybe we popped them up here. For example, maybe we pop some electrons up there. And what will happen is that once they're up here, they have too much energy. They don't want to stay there. And so they will start dropping down. And the same one can make several different drops. Or sometimes this one might just drop directly down. It kind of depends, okay? On the exact level and some other stuff, but and some of it's just random chance. But if we happen to get one up to this level, this particular level, my third level. So if we number these, n equals 1, n equals 2, n equals 3, n equals 4, etc. So we're just going to give a number for each of these. If we happen to put it at n equals 3, and then it drops to n equals 2, this transition itself will release red light. This is the perfect amount of energy difference to correspond to a frequency which matches red light. Okay? And so that is the light that we see. It'll also release other colors. So let's see what I forget exactly how I phrased the next slide. Oh, we're doing the Rydberg stuff. So we'll do that. It can do other colors as well. We'll talk about that. No, we'll talk about it here. Here, between 2 and 1, this is a bigger energy drop, right? So a bigger energy, bigger E, will correspond to a bigger frequency. We'll probably see something more like blue or purple. If we're here, between 4 and 3, this is a tiny energy drop. So with small energy goes with small frequency, it actually will be infrared. Okay, so you can get different colors from these different transitions. I love it. Frankie says, crazy how this stuff works. I know, I love it. It's amazing. This is why I love physics, is because stuff like this is so cool. All right. So we actually have an equation for this, which I want to go through for you guys, where we can predict exactly what our wavelength will be. So instead of frequency, we're going to talk about wavelength, but again, the two are related. So if you know the frequency of light, you know its wavelength, and vice versa. So as a reminder of that, it comes from the fact that the speed of light is frequency times wavelength. This is our constant 3 times 10 to the 8th. So if you know frequency, you can calculate lambda and vice versa. All right, so the Rydberg formula here, if you ever take a chemistry class, they might talk about this as well. This is kind of where we do atoms, kind of overlaps chemistry and physics. But it lets us figure out what color will be released between different energy states for hydrogen. Only works for hydrogen, but it does work. It's pretty cool. It looks more complicated than it is, okay? So it looks a little bit intimidating for people, but I'll talk you through it, okay? So lambda here, that's what our goal, looking for wavelength. Capital R is a constant. So its value is listed here, 1.097 times 10 to the 7th. Its units are 1 over meters, right? Because wavelength here is 1 divided by meters. So this has the same units, 1 divided by meters. Then in parentheses, we have 1 over n squared, 1 over m squared. N and m are just referencing which energy level. So when I drew these before, I said this was like n equals 1, n equals 2, n equals 3, maybe n equals 4, etc. And so you might be like, oh, well, yeah, I know what n is. M is going to be the same kind of thing. It could be any of these as well. So for example, for this one, from 3 to 2, which I'll show you how this works, this would be m equals 3, n equals 2. Because we always choose m to be, m just represents what state do you start from. N is where do you end up. So m is going to be big, n is going to be small. Okay, because we're always going to look at transitioning down, where you lose energy to spit out light. Okay? All right, so I told you guys that this is, the 3 to 2 is our red transition, and I want to prove to you that that works. And I have on the slide that red light should be about 656 nanometers. Okay, let's see if we can get there. All right, so I'm going to come over here, and I've got 1 divided by lambda equals, so for R, I'm going to plug in this number. Make sure I get the positive 7. Okay. I'd say one of the big mistakes I make is I tend to write negative 7 there, but it's not. It's a really big number. And then I'm going to come in here. N is my smaller one, so that's 2 and it's squared. Minus M is my bigger one, 3 and it's squared. So I highly recommend find this value first. Okay, if we plug this in to our calculator, you can either just plug in as it's written, or you can recognize 2 squared is 4, 3 squared is 9, right? So I'm going to do 1 divided by 4 minus 1 divided by 9. And I get 0.1388. Right there. Okay. Now that's just a number, and we can multiply it by this big number. So that'll give me 1 divided by lambda equals, so I'm multiplying 0.138 times that value there. So times 1.097 times 10 to the 7th. And I get 1.52 times 10 to the 6th. But we're not done because we're looking for lambda. So in order to solve for this, whenever you have 1 over a thing and you want to solve for it, you take the reciprocal of both sides. So lambda will equal 1 divided by 1.52 times 10 to the 6th. Let me see what I get. So I'm going to do 1 divided by all of that. Make sure I put parentheses in. I get 6.56 times 10 to the negative 7th, and I know my units are meters, okay? Because my Rydberg constant had been in 1 over meters. So I take the reciprocal of that, I get meters. Okay, so 6.56 times 10 to the minus 7. Let me check this against my 656 nanometers. All right, so 656 nanometers, that'll be times 10 to the minus 9. Because that's what nano means, is 10 to the minus 9. And yeah, these are going to be the same because if you move this decimal point over by 2, this has to get smaller by 2. It's like we're dividing both sides by 100. Thinking about that, dividing the whole thing. It's because you're writing it in scientific notation, right? Yeah, so those are going to be the same. This gives us the answer we find experimentally. Awesome. Okay, so I'm going to give you guys a couple minutes to try this for yourselves and to see what you get for the transition between 4 and 2. And I will be right back. Okay, I'm back. Oh, Frankie reminds me about the quiz code. Thank you. I have that up. Let me grab it and put it up there. Seven 0 2 3 5. Okay, so there it is. There's your code. All right, so Frankie got 486 nanometers. That sounds right to me, but let's just double check and make sure everybody can follow along. So when we look at this, our process here is going to be the same. We're now doing from 4 down to 2, like that, which is a bigger energy drop, which means it's a bigger frequency, should be a smaller wavelength. Okay, so when we come in here, n is the same. We still ended up on 2. It doesn't have to be 2. It could have ended up somewhere else, but for these problems, it's 2. But we're starting at 4, so that's what changes. This becomes a 4. So now, when we plug in our values, instead of a 9, it's a 16, so that's 4 squared. And again, you can find this number first and then multiply it by that. You will get, I'm going to go ahead and do the multiplication here. I get 2.06, 06 times 10 to the positive 6, and then the wavelength will be 1 divided by that. And I did get what Frankie got, which was 4.86 times 10 to the minus 7 meters. And that is blue light. Blue usually is in the 400s, maybe 450-ish, and we're kind of near that, 486. So this is going to be a blue light that you would get from that. All right, so I will ask you guys this question. Again, obviously there's no poll, but if we went from 4 to 1, what could we get? Okay. So when we go from 4 to 1, this is an even bigger energy difference than from 4 to 2, and certainly much bigger than 3 to 2, right? We're literally looking at what is the size of the gap in between these. So this is a huge energy, and so really the question becomes, which of these colors has the biggest energy? Well, blue is bigger energy than red. We need to go towards the blue side of the spectrum, but we have actually even more energy than blue, so this would be ultraviolet. So if an electron is in the 4th state and it transitions all the way down to ground state, we wouldn't see that with our eyes. You can measure it with a detector that measures ultraviolet light, but we're not going to see every possible amount of light that you can get from hydrogen. Yeah, Frankie guessed ultraviolet. Excellent. So here are some pictures of what we would see. This is just the visible light part for different elements. So for hydrogen, that red line represents all of the red light that we get from the 3 to 2 transition. Then there's kind of a greenish blue line, and then a really blue, and then kind of a purple. And those are from some of the other transitions that we get kind of in this range, right? We're not going to get any here. This would be infrared, right? This is the smallest energy that we're going to be able to see. But then as we get a little bit bigger, pretty much as we land on the 2, those are still colors we can see, right? This is blue, like this might be like probably the greenish one, and then up here is going to be more of a true blue, and then the next one would be purple. But if we were to transition all the way down to 1, that becomes ultraviolet, we don't see it. Okay. Hydrogen is not the only element that does this. These are pictures of mercury and neon, which give different colors. If you look at mercury in a tube the same way we would hydrogen, it would glow very much a blue color because the blue is the strongest line, right? It gives off some red, but it's weak. It's not very much. And the intensity of the color is related to how often do these transitions happen. So if you put the energy into the electrons and they jump up to 3 and fall down to 2 all the time for hydrogen, we get a bright red light. Mercury's lines are in different places, right? We see different colors from mercury than we do from hydrogen. And that's because the energy levels will have different values for different elements. So it gets much more complicated, as you get to atoms with more than one electron. Because in hydrogen, you only have one proton, one electron. And they interact with each other. That's fine, we can figure that out. Helium, though, even, you've got 2 protons in the nucleus. Sure, that's fine, it's still just a positive thing in the middle. But now you have 2 electrons, they interact with each other. And that changes their energies. Okay? Anytime you interact with something, there's energy involved. And so those interactions with the electrons with each other make these energy levels more complex than they are for hydrogen. And you get lots of different colors. Neon's really cool because it has so many of these in the red, orange, and yellow. And that's why they call neon lights, because you would put neon gas in them, run the electricity through, glows bright orange. Okay? All right, so Bohr's model's pretty good for hydrogen. Bohr's model cannot, in fact, replicate, it gets these numbers perfect for hydrogen. It doesn't get them at all for anything else, okay? So how do we improve this? Well, we start treating it more like quantum mechanics. And this is going to start to get into what I was talking about a little bit last time, where we were like, oh, light is a wave. And I'm always like, yeah. So light is a wave. Except when it's not. So it and other things, we've got kind of 2 very distinctive, different kinds of things in our universe. We have waves, we have particles. So things that are waves include sound waves, water waves, waves on a string, waves in a slinky, earthquakes, right? Those are all waves, and you can tell a wave is a wave because it stretches across, see all this space that it stretches across? And there's some medium that we have where those things bounce up and down, but it's not in one place. It covers a lot of space. A particle, on the other hand, is something like a ball, or even a person. Like, I am just a single object. I exist at one spot, one place in space. And there are other differences. When a wave gives energy to something, it does so in this very, continual way. So you can think of, if you have, a buoy on the water, right? And it's sitting there, and this wave comes by, the buoy would lift up and come down. And as it lifts, it would gain potential energy, and then it would lose it. But, that takes time, right? On the other hand, my particle, when it gives energy to something, it's like one instant, right? If I drop this on the floor, that impact is the moment when I give energy to something, right? If I grab it, that moment I grab it, I feel it hit my hand, that energy goes into my hand, right? So particles and waves are opposites, sort of in the classical view, where in terms of how much space they take up, it's opposite. Lots of space, one point. How they give energy is opposite, like slow and continuous, versus at one moment in time. The problem is, when you start getting into... Is my thing going to advance? It's gonna be, annoying. When you get into quantum mechanics, things aren't so cut and dried. Okay, so we talked about this with light. We looked at the double slit, right? So when you send light through a double slit, it makes these vertical patterns of light, dark, because it depends on if the waves match at that point, they will construct and be bigger and brighter. But if they're ever out of phase and they're opposite of each other, it destructs and it creates a dark spot. So we can use this experiment to prove that light is a wave. All right. Now let's do that. This same experiment, we're going to do it with electrons instead. So I will make this big. See, my internet's being slow. Okay, but here you can start to see what's happening here. Actually, let me pause it for a second. Is that we are sending electrons through a double slit. So instead of light waves, instead of like a laser, we have a beam of electrons. And these electrons come through the slits and they hit the detector, which is what we're seeing. So every bright spot is where an electron hits the screen. And it does so in a way where it deposits all of its energy at a single moment. Okay, so it's like a tennis ball hitting a wall. The electron hits the detector. That impact, the electron gives all of its energy to the detector. Okay, and it leaves a single spot. So our electrons are acting like particles. Let's see what happens as this experiment continues. And it will speed up eventually. There we go. So the electrons seem to be hitting at kind of random spots on the detector. But as the experiment goes on, there are some spots where they're a lot more likely to hit than others. So these are thousands of electrons. They're each going through the double slit. And they each impact and give their energy all at once. But as they do that, as it accumulates, you can see the pattern that is created, right? We've got light, dark, light, dark, light, dark, light, dark. And that looks just like this, right? So this picture of what the light looks like, is exactly what's happening with the electrons. And so this is one of the key mysteries / really cool things about the world we live in, is that at microscopic scales, sort of like water waves or sound waves and tennis balls and people, things behave either like waves or particles. But at the very small atomic scale, things act like both. Okay, so this electron goes through the double slit, and when it impacts, it gives its energy like a particle. But the pattern it creates is a wave pattern. Particles don't make that pattern. They would just kind of fill it up randomly or just shadow the two slits depending on how you set it up. This doesn't do that. It looks like a wave pattern. And the reason for that is that fundamentally, this electron is not just a point, it is also a wave. It's a kind of wave that can give all of its energy at once. And it's the kind of particle that can interfere with itself to either, be bright or dark. And for the electron, it ends up being the probability that it lands there. Because fundamentally, when we start asking ourselves, if I have an electron and it's kind of like a wave, and we ask, what's waving? The answer is probability, okay? Fundamentally, our universe is built on kind of randomness and like how likely is it to happen? Well, then maybe it will happen that way. But there's chances it could happen a different way. And that's how our universe works at the smallest scale. Now you build up enough of that to the biggest scale, and we don't work that way. Like me, it's not random, it's Newton's laws. For an electron, it's more random. It's one of my favorite experiments in the whole world, by the way, guys. It's just so cool. All right, so this comes back to kind of how we can make the Bohr model work. Because one of the weird things in the Bohr model was that issue of the orbits and the stationary orbits. And basically I said, like, we know that we can't let the little point particle electron move in a circle because it will just fall into the nucleus and you don't have an atom anymore. But Bohr was like, okay, so we won't let it. And the question becomes like, well, how do you enforce that? How do you force this electron to stay in this circle and only this circle and not, or maybe also this one, but not a circle in between, right? Like what makes the Bohr model work? And the answer is waves, okay? So I'm going to attempt to draw this, although the drawing on your slide is way better. But the idea is the electron is not going to be at a point, it's going to be a standing wave. Okay? So standing wave, we've got like the nodes and the antinodes. Oh my God, I did it. I did it. I drew a picture. I'm way more proud of this than I should be. Okay, so here's a down part, and here's a down part, and here's a down part, and there it is. So this is like 4 wavelengths that fit in this circle. And it's a standing wave because it could have been the other way. So anything that's happening here, this is an antinode, so you have big wave amplitude. Anything here is like a node. Okay? So in essence, your electron is not necessarily going to be just that point. It could be a wave. And when you put it around an atom, you say, now you have to create a standing wave. And so 4 wavelengths can fit here. And maybe when we go smaller, we get 3 wavelengths. Smaller than that, we get 2 or maybe 1. But we're not allowed to have half wavelengths. And so, or like a quarter or a third or 0.782 of a wavelength. You'd have to have an integer number of wavelengths. Well, that's like our energy. Like if it's an integer number, that means there are going to be gaps in between where it can't exist. That's what we observe. Now, the other interesting thing here is the de Broglie relationship. So this is pronounced as French. So it kind of looks like de Broglie, but it's not. It's de Broglie. He's French. He was actually a prince of some kind, but he liked physics. And he figured out that basically people with experiments were figuring out that light had both wave properties and particle properties. And he was like, well, if that's true of light, maybe it's true of electrons. And so he said that you could relate the wavelength of the electron, what we normally think of as a particle, to the momentum of that particle. And so depending on how fast it's going or what orbit it's in, you'll have these different wavelengths. Okay, let's see here. Oh, it's being slow. I was like, I know I have another slide. So we're not going to, I would say we're not going to worry too much about this relationship, except that this H here tells us that this wave particle weird thing only happens at the small atomic scale, because this is times 10 to the minus 34. It is very tiny. If you have a normal amount of momentum, like maybe you are a person who is walking, you might have a momentum of like 80 kilograms times 1 meter per second. So you'd have 80 kilogram meters per second here. So 10 to the minus 34 divided by 80 is so small. This wavelength would be so tiny The only way you'd be able to measure it is if you could fit a walking person through slits about the size of their wavelength. So you'd have to fit through a slit billions and billions and billions of times smaller than an atom. That's not going to happen. With electrons, their momentum, their mass is so tiny, right? The mass of that electron was 10 to the minus 31. So they can have a momentum such that it's really tiny, and h divided by that gives you a wavelength that we can measure, right? You can make a slit that's a millimeter or a tenth of a millimeter across, and the electron goes through it, and we see this wave behavior. So that's the important thing with this equation. It's just understanding that it can help us see whether or not we'll measure those waves, because you can only measure waves with the double slit experiment if the slit is roughly the same size as the wavelength. All right, so our last slide today is, I said we would talk about the best model of hydrogen before the end. Well, here it is at the end. So the Bohr model is really good, but it doesn't give us everything. A better model is our quantum mechanical model, and this was developed by Schrodinger, the Schrodinger equation. And basically, it takes the idea of standing waves, but we get more complex patterns. It's not just a single standing wave in a circle. But I did want to show you this because this is the best representation of hydrogen that exists. So on the left, that top left picture, you've got the red dot in the middle, that's your nucleus. And then the black dots represent where are you likely to find the electron. So it does not represent an electron, it just represents probability. If you measure, where are you likely to find it? Well, you're likely to find it kind of in the middle. Okay? And that is actually the ground state of of hydrogen. So that was our smallest orbit, and we're most likely to find it closest to the middle. That makes sense. The next picture, that kind of looks like you've got the center part that's gray and then a clear bit and then a gray ring. That's going to be one of the excited states, okay? Where you might find it in the very middle, or you might find it kind of in a sphere, technically, these are three-dimensional. You might find it further away. And so that's going to be that more excited one. But they're not always actually spheres. So with hydrogen, depending on what's going on, sometimes they'll be biased towards like one space or another. And so the bottom one shows what's called a p orbital. If you ever do chemistry, these spherical ones are s orbitals. The lobed ones are p orbitals. And you get more complex like dumbbell shapes and stuff for d orbitals. But the p orbital is biased. It's either going to be on one side or the other, but never in the middle. And again, that looks like a standing wave. You've got like high amplitude antinodes where you're likely to find it, and then nodes where there's no probability. You don't find it there. Okay. The other picture shows kind of a slice through, like the first pictures are kind of like a plane through the sphere of the atom, and then what we're going to do is take a slice through that and just look at like how big is the probability. So the gray curve, actually let me draw this, corresponds again to the ground state. So for the ground state, we have our positive in the middle, and then we're most likely to find it somewhere around like that, right? So what this graph shows is this is distance, kind of distance from center, and this is probability. And so for this one, we are most likely to find it near the center, so we have like a big probability and then it dies off. So where are we going to find it? We're going to find it right here. And actually what's cool is that this distance is the same distance that Bohr predicts with his model. So they do kind of correspond. They're not completely different. But what I think is neat is what happens again when you go to a more excited state. So for the excited one, we now have like several rings. So we've got like a little probability that you're here, more probability that you're here, and a little bit more probability that here, that's what the kind of yellow one with the multiple rings is saying. And so what that looks like is we've got a small probability that you'll be found really close to the center, and a slightly bigger probability that you'll be a little bit farther away, but most of the time you're kind of way out here. So as the higher the energy gets, the more likely you are to be further away from the nucleus, which is the same thing that Bohr tells us. But maybe we'll find you here. So this is why this is a better model than Bohr's, because this matches experiment better than Bohr's does. Okay. But the mathematics gets really complicated, although you'll have to trust me, it's really fun to do this. But we can exactly mathematically solve Schrodinger's equation for hydrogen. But only for hydrogen. So once you get into really complicated atoms like helium with 2 electrons, we don't have exact solutions. We have approximations, which work pretty well as well. So that is our tour of atoms and our different models. So we talked about why we know the different pieces exist, and then kind of the development of the models from that as well. So that is it for today. Have a good one, everybody, and we'll do nuclear stuff next week.